Hello everyone. Welcome back to another session under the course CMOS VLSI Design. Today's topic that we are going to see is transmission gate and its electrical characteristics. And I am Dr. Sangeeta, working as Assistant Professor at Vardhaman College of Engineering. Let's continue with our topic. As the topic suggests, that it's a transmission gate. So before we go in depth of what exactly is a transmission gate, let me give you a brief overview. We have MOS transistors, PMOS transistor and NMOS transistors. And we know that a PMOS transistor is able to transfer logic 1 correctly but not logic 0. The same thing applies for NMOS transistor, where it can transfer strong logic 0 but not logic 1. So these are the drawbacks when I use only PMOS transistor or NMOS transistor for the design of my circuits, because PMOS will be transferring, if I take only a PMOS transistor as a switch logic or a pass transistor, it will transfer strong 1 because we are using it as a pass transistor, so it has to transfer logic 1 and logic 0. Now coming for the only PMOS transistor, if I take it, it will have strong 1 it will be able to pass and weak 0 it will be having. Quite similarly, if I take a NMOS transistor now, it will be able to transfer the vice versa case, strong 0 will be transferred but weak 1 will be obtained. Now if you see this, when I use only PMOS transistor or only NMOS transistor, there is a limitation on how the logical levels of logic 0 or logic 1 is being transferred, because one transistor is transferring correct logic 1, strong 1 but weak 0, and NMOS transistor is giving me strong 0 but weak 1. So to overcome the drawback of these two individual transistors when used in switch logic, there has been a new type of switch logic that has been introduced, which is known as transmission gate. This is in short known as TG. So a TG is built having a parallel combination of a PMOS transistor and a NMOS transistor. So a transmission gate is obtained by taking a parallel combination of PMOS transistor on top and NMOS transistor. And on the left side, a PMOS transistor and NMOS transistor are in parallel to form a transmission gate. On the left side I have my input and on the right side I have my output. Because it is acting like a switch logic now, it means that whenever TG is in on state, whatever is input on the other side, that will be passed on to the other side, that is the output side. So logically we say that when X is equal to 1, because the gates of PMOS and NMOS are receiving the complementary signals. So when gate of NMOS is receiving a signal of X, the gate of PMOS is receiving a signal of X bar. That's how I can take the control value of X now. So suppose I substitute X equal to 1 here, then this NMOS transistor is on. Similarly, PMOS transistor is also on because X bar is equal to 0, and we say that our TG is in on state. When TG in on state, because it is acting like a switch logic, a switch is the one that transfers whatever is present on one side to the other side, input to the output. That's how I say that Y will be equal to A. Under which condition? When X is equal to 1. That's how the transmission gate expression is written as Y is equal to A into X, where A is my input that has to be transferred and X is the control signal. This is the generalized expression for my output across a transmission gate. Now coming for the symbol of my transmission gate, the symbol is drawn. Let me draw the basic symbol. Transmission gate is bidirectional in nature. So I have two buffers drawn on either side. That is how my signal or the symbol is taken. Input is on the left side, output is on the right side. I have a control signal at the bottom, that is gate of NMOS as X bar and gate of PMOS is on the top, that is X bar. So I have a symbol of my transmission gate. Input is X. X is the control signal given to NMOS, that is X. PMOS is receiving X bar and Y. So now if you see the brief part of the transmission gate, it is having two transistors in parallel, one PMOS and one NMOS. This is what is my basic expression across the output of my transmission gate, and the extreme right side is my symbol of the transmission gate. And the advantage of transmission gate is it overcomes the drawback of individual PMOS transistors, because individually they are unable to transfer both the logics correctly. So the TG, when it is used in logical styles, we see that it will be able to transfer strong 1 and also strong 0 because of the presence of both the transistors, which are NMOS and PMOS. That is what is the advantage of our transmission gate. This is the brief overview of transmission gate. Now let us move for the electrical analysis of transmission gate. As discussed just now, that it is able to transfer both logic 1 and logic 0 correctly. Now let us see how the transistors are operating when your transmission gate is transferring logic 1 and when it is transferring logic 0. So my next part will be now logic 1 transfer across transmission gate. Now logic 1 across transmission gate, I have drawn the circuit here. So as we have seen in the previous slide, here I have a NMOS transistor. Let me write it down as Mn, and here I have a PMOS transistor MP. Then input, because I am transferring logic 1, input to the transmission gate is VDD. Because I am transferring logic 1, so high voltage VDD will become my input. This is my output taken across a capacitor. So output logic 1 or logic 0 will be obtained by charging or discharging of the capacitor. Now if you see this complete circuit diagram, because it is logic 1, just before we have discussed that PMOS is able to transfer logic 1 correctly. So the source of PMOS is represented here. If this is the source, the other side becomes a drain, and gate is connected to ground, because we know that to start my PMOS transistor, 0 has to be applied. That is why gate is receiving a logic 0 signal, which is ground signal. Same thing if I take my NMOS transistor now. For NMOS transistor to turn it on, gate is connected to a positive voltage VDD. Now the drain terminal and source terminal are represented for the logic 1 transfer. Now what we have to do the analysis here is, we have to determine the operating regions of the respective transistors, whether they are in cutoff, whether they are in saturation or in non-saturation, and based on what conditions they have been decided. Now let us mark the voltage levels. For NMOS transistor, we need V, G, S, N. So gate is positive, source is negative. Similarly, for VDS, I need VDS. So drain is positive, source is negative. This is for my NMOS transistor with the suffix of N. Same thing if I have to take it for PMOS transistor now. For PMOS transistor, I take VSD. So this is plus, this is minus. The gate to source voltage for PMOS is VSG. So I write here VSG. This is plus and this is minus. Now let us do the analysis of my transistors. Let us take, suppose I am taking my NMOS transistor first. So to determine the operating region of my transistor, I have to first determine the VGS voltage, VDS voltage, and that's how I have to determine the operating regions. So let me write here VGSN, because for NMOS, and VDSN. Now, what will be the value of VGSN for the NMOS? VGSN means it is VG minus Vs. So, VG of NMOS is connected to VDD, S of NMOS is connected to Vout. That's how VGS will be now VDD minus Vout. VDD minus Vout. Similarly, let me write down for VDSN. Drain of NMOS is connected to VDD. Source of NMOS is connected to Vout. So this is again VD minus Vout. VD is connected to VDD minus Vs, which is connected to Vout. So I have written both the voltages here. Now what is the condition to determine saturation and non-saturation is, I have to take VDSN on left side, VGSN minus VTN on the right side. And we know that if I write a less than relationship here, I say that my transistor is in non-saturation. If it is greater than or equal to, I say that it is in saturation. So let us figure out what is the condition here. So from here I can write VDSN is VDD minus Vout. Right? Similarly, VGSN is also VDD minus Vout. Minus VTN is existing. Now from here, if you see the conditions here, right, I can say that Vout, because Vout is the one that is obtained across capacitor voltage, Vout initially, because I am taking it as charging part, initial voltage across capacitor, I'll write it down as 0 because I'm transferring logic 1. So initially I'll assume that capacitor voltage is 0. Slowly it is rising to a voltage of VDD. So now, so initially if I take it here, Vout is a smaller value. So obviously VDD will be greater than VDD minus VTN. So I will be having a greater than relationship here. Greater than relationship here. So if this is greater than, I say that my transistor Mn is operating in saturation mode. That is what I can make a inference from the relationship. So till which point it is in saturation region, that also we have to figure out. So in the output, we will be having a limitation for NMOS that it can transfer till VDD minus VTN. So suppose I cross VDD minus VTN, what will happen to this relationship, or what will happen to my VGS voltage? So when Vout is equal to VDD minus VTN, I got to know that VGSN voltage, right, from here, it is equal to VDD minus Vout, right? So Vout is equal to VDD minus VTN, I have to substitute. Then if I expand it, I see that this VDD and minus VDD will be cancelled, and I have VGSN as equal to VTN. So what do we understand from here? So when Vout is increasing, right, beyond VTN, this minus VDD minus VTN term will be increasing further, thereby decreasing my gate to source voltage. If your gate to source voltage goes below VTN voltage, you say that your transistor is going into cutoff region, because unless until my gate to source voltage crosses the threshold voltage of my transistor, I can't say that my transistor is in on mode. So when gate to source voltage of NMOS is going below the threshold voltage, my transistor Mn is entering into cutoff. So for analysis of Mn transistor, we got to know that from initial part Mn is into saturation mode. It will be in saturation mode until I cross my output of Vout, which is VDD minus VTN. Thereby, it will enter into cutoff region. Now, similar analysis, we have to do it by taking the case of my PMOS transistor. So, let us see that. Now let us take our transmission gate again, and let us do the analysis for the PMOS transistor. So, for MP, if I take it, process is again same. I am doing it for logic 1 transfer itself. So what do we have for PMOS transistor? Take the conditions again, write down VSGP, which is equal to now VSGP, G is grounded, Vs is connected to VDD. So I'll write here VDD. Similarly, VSDP now will be written as S is connected to VDD and drain is connected to Vout. So I'll write it down as VDD minus Vout. Now let us determine the operating region for this. So again I'll take my condition. LHS is VSD, RHS is VSGP minus mod VTP. Substitute the conditions here. So this is now VDD minus Vout. VSG is VDD minus mod VTP. This is one term on LHS, this is one term on RHS. Now, if you see the relationship here, let us take the starting point. Your output is increasing from 0 towards high voltage. So if I draw your output curve here, first output is 0. This is for my output. Maximum voltage is VDD. Then I have a point for VDD minus VTN. Then here slowly the output is increasing, so I have a threshold voltage of PMOS transistor. This is what I have the regions marked onto the output voltage, and your output is charging from 0 and going till VDD. So what I have to do is here I have to mark and mention the operating regions of the respective transistor. So let me write it down here so that parallelly I can write down the operating modes. MP indicates PMOS and MN indicates NMOS. Now, when you see this curve, output is rising from 0 and going till VDD. So when I have a 0 here and till VTP, it's a smaller voltage. So when output is a smaller voltage, obviously VDD minus Vout will be a greater value when compared to VDD minus VTP. So what will I have? I'll have a greater than relationship here, because initial voltage output is starting from 0. So I'll be having, if I substitute here 0, it is VDD is greater than VDD minus VTP. Suppose I substitute the limiting condition of mod VTP here, it will be VDD minus mod VTP on LHS and VDD minus mod VTP on RHS. So for both these conditions here, I'll be having greater than or equal to. So I can say that between these two regions, your MP transistor is operating in saturation region. Saturation region. Now what will happen when my voltage, output voltage increases beyond the VTP voltage? So if your output is increasing beyond VTP, then output is increasing now. So the difference between VDD minus Vout will be what? It will be a smaller voltage. So when output is increasing, the difference is decreasing value. So the relationship will be the VDD minus Vout, this term, when output is increasing, will be less than the right side term, which is VDD minus mod VTP. So obviously when this condition is satisfied, I say that my transistor MP has entered into non-saturation region. Non-saturation region. So where is this particular condition I have to write? After mod VTP, your MP transistor is entering into non-saturation. So I'll write here non-saturation, and beyond this also it is in non-saturation. What was the conditions for my MN transistor that we have taken previously? In the previous discussion, I got MN transistor was in saturation. It was in saturation only. Beyond VDD minus VTN, MN entered into cutoff region. So I have done the electrical analysis for logic 1 transfer, where we have taken our case of NMOS transistor and PMOS transistor, and we have done the analysis using voltage levels, and that's how we got to understand where the transistors are operating. Now based on the operating modes of your transistor, whether it is in saturation or in non-saturation, you have to write down the respective current expressions, because if MP is in saturation, write down the saturation current expression for MP. If MP is in non-saturation, write down the non-saturation current expression for MP. This is how we do the electrical analysis of logic 1 transfer through transmission gate. Now quite similarly, let us do logic 0 transfer also. Let us see now the logic 0 transfer across the transmission gate. I have just redrawn the transmission gate here for you to understand. So it's a similar PMOS transistor on top, NMOS at the bottom, and they are in parallel. Gate of NMOS, because NMOS has to turn on, and gate of NMOS is connected to VDD and gate of PMOS is connected to 0. It is logic 0 transfer. So input here will be equal to 0. Output is taken across a capacitor. So I'll write C out. Because output is going to 0, it's a discharging voltage. So I write down V out initial value is equal to VDD, because initially it is at VDD and that's how it is discharging and coming to a value of 0 voltage. Now let me mark the terminals again, because I am transferring logic 0. This will become, because it's a logic 0 transfer, and 0 will be transferred from NMOS transistor. This is becoming source, this is becoming drain, and this is as usual the gate terminal. For PMOS transistor, it will be the opposite. This is drain and this is source. Let me write down the terminals also. So for NMOS transistor, I write it down as VGS. So gate is positive, source is negative. For NMOS transistor, I write down VDS. So this is minus and this is plus. Similarly, let me mark it for PMOS transistor as well. So this is my gate region. For PMOS transistor, I write down VSG. So gate is gate is minus, VSG. So plus is here, minus is here. Then VSD. So S is plus, D is minus. Let us do the similar analysis for my PMOS and NMOS transistor. So let me take again our MN transistor. So write down VGS now for NMOS and VDS for NMOS. Now VGS, from your diagram, VG is connected to VDD, VS is connected to 0. That's how it is becoming equal to VDD. Then similarly, if I want to write VDS now, VDS, drain is connected to V out and S is connected to ground, that is 0. So this is equal to V out. V out. So we got the values as VGS is equal to VDD and VDS is equal to V out. Let us figure out how to determine again the saturation or non-saturation region. So I have to write down my condition back again. So conditions as we know it in better way, VDS is here and VGS minus VTN is on the other side. So let us write the voltage values. VDS, I got it as V out. VGS, I got it as VDD minus VTN. Now to find out what is the operating region of my transistor, V out, initially it is starting from VDD and slowly it is decreasing. So obviously V out is a greater value when compared to VDD minus VTN because it is starting from a higher value. Because V out is greater than this term, I say that your MN transistor is in saturation region. Quite similar to what we did for logic 1 transfer, I also have here the same voltage levels. I have a 0, I have mod VTP, I have VDD minus VTN, and I have VDD. Output is falling from VDD to 0. That is what is the direction. Now when Vout is decreasing further and crosses the VDD minus VTN term, we see that Vout will become a smaller value when compared to the RHS side. That's how I say that when Vout becomes less than VDD minus VTN, your transistor Mn has entered into non-saturation region because of the condition where VDS is less than VDD minus VTN. Because this condition is becoming less than now, your transistor is entering into non-saturation. So let me write down here what did we get. Mn, initially it is in saturation. After crossing VDD minus VTN, Mn has entered into non-saturation and the same thing continues thereafter. This is what we got it for the NMOS analysis. Quite similarly, let us take my PMOS transistor and let us do the analysis. So now let us see the logic 0 transfer by taking the analysis of PMOS transistor also. Now for PMOS transistor, what we have done for NMOS, let us do the same thing for PMOS transistor. So for PMOS transistor, we have to take the voltages VSG. So this is plus and this is minus. So VSG, if you write it down from the circuit, S is connected to Vout, G is connected to ground. So I'll write it down this as Vout. Then what is happening to VSD now? VSD, S is connected to Vout, drain of PMOS is connected to ground. So this is again equal to Vout. So if you see, whenever VSD is equal to VSG, or if you write down the condition of saturation, I can clearly say that your PMOS transistor is in saturation region. PMOS is in saturation region. Now, till when this will continue in saturation region? So, let me mark the output voltage that we have marked it previously. This is 0. I have mod VTP. Then I have VDD minus VTN. And I have VDD. For the previous case, we wrote our Mn transistor operation. Mn initially it was in saturation, then it entered into non-saturation thereafter. So I'm just writing it here. Now let us write down for the PMOS. So for PMOS, I got to know that from the analysis it is in saturation. So I'll write down here PMOS is in saturation, PMOS is in saturation till which point? Till it is greater than the threshold voltage. If it goes below the threshold voltage while decreasing the output voltage, obviously it will enter into the cutoff state. So this is how, if you see the characteristic curve here of the Vout, this is for the output voltage. The same we have done it for logic 1 transfer. You see that here I have 0, VTP. Within this range, MP is in cutoff region, Mn is in non-saturation region. Beyond this, Mn is in non-saturation, MP is saturation. And for the first two, both are in saturation. And because it's a logic 0 transfer, output will be starting from VDD and it will be falling towards the 0. This is how your capacitor at the output is getting discharged, and we say that logic 0 is transferred via the transmission gate. So we have seen today the analysis of your transmission gate and how the logic 1 and logic 0 is transferred across the transmission gate, and what are the operating regions of the respective transistor. Thank you. We'll meet again for the next session.